Um, so in the class on Monday, we were speaking about class definitions in OWL, and we saw some set-based definitions which relate to intersection, to union, to disjoint union, to complement of, and to one-off. It's where we define effectively all the members of the class. So to continue, we have a few more features that where we can define a class in terms of some of the properties that its instances have. So for example, here we define that a person is a subclass of, and here we have a new definition of a class. It's the class of things whose parents are people. So all of their parents are people. So this says that all of is effectively, if we read it in more natural language, it means that all of the parents of people are people, or all the parents of person are person. So we say person subclass of all values from person on property has parent. So what does this mean? This means that if we have Mary, and Mary is a person, and Mary has parent Michael, then we could infer that Michael is a person. Okay. So here we use subclass. So we might be tempted here to consider using it in both directions, which is to say that if you're a person, then all your parents are people, and to say also in the other direction, if all of your parents are people, then you must be a person, right? However, it actually doesn't work in both directions. This example, and most examples don't work in this direction, in the other direction. And this is because if you have no parents, if you could not just no parents in the data, but if you can prove that something has no parents, then in this case, you could prove that it's a person. Because if you have no parents, then trivially all of your parents are people, right? So how would that work? For example, if we had Choppy, and Choppy was a lawnmower, and we knew that lawnmower was a subclass of has no parents, effectively. So this, we somehow know that lawnmowers can't have parents. Then what does this entail? Any guesses? So if we know that Choppy is a lawnmower, and we know that lawnmowers have no parents, that's what this here denotes, that it does not exist a parent, it has no parents. So then Choppy has no parents. And if Choppy has no parents, then it's trivially the case that all of its parents are people. So this for all is satisfied if there doesn't exist anything, right? So if it's the empty set, if there's the empty set of parents, then it's satisfied, right? So similar to first order logic, for example. So this tells us that Choppy is a person because all of Choppy's parents are people. It has no parents, so it's trivially true. So it's a little gotcha, or sometimes people mistakenly might define something like this, right, in both directions. So this is not suitable in this case. So we need to be careful using equivalence with all values from. Okay, so here's the argument I mentioned. If all of X's parents are persons, then X is a person. This is what this tells us now. But Choppy does not have any parents, so its parents are trivially anything. So all of its parents are trivially whatever class. This Choppy must be a person. So, okay, so we're rarely going to use this sort of equivalence here. Now, we could solve that by saying that it's equivalent to the intersection of all values on has parent is person and is human or animal or something like that. We could add something more here to complete this equivalence, but just this alone would not be a good idea. If we have all values from the for all quantification, what about the exists? So we also have the version of exists where we say, for example, a parent is equivalent to has child person. So in this case, what we're saying is an equivalence. So we're saying it in both directions. That a parent means that if something is a parent, then it has a child that's a person. On the other hand, if something has a child that's a person, then it's a parent. Okay. So this means that if Michael has child Mary, then Mary is of type person. Sorry, if Michael has a child Mary and Mary is of type person, then we can entail that Michael is a parent, right? Because there exists a child that's of type person, therefore Michael is of type parent. What about in the other direction? So we have this equivalence. So what happens if we say that Michael is a parent? What could we infer here or entail? So if Michael is a parent, we know that Michael has a child and we know that that child is a person, okay? The thing is, we don't know who that child is. We don't know who is this child here. So it's sort of like an existential node. There exists something here, right? But we don't know what it is. And we can represent this in RDF as a blank node, for example. So Michael has child someone and someone type person. Okay. So we can entail the existence of some things, even if we don't know their identity. Any questions or doubts about some values from or all values from? Oh. Okay. There are arguably two of the trickiest features that L has. Next, we have has value. So has value is effectively similar to saying that, okay, we'll look at the example first. So this says a person is a subclass of there exists species Homo sapiens. The difference here is that this is not a class, but rather it's a value, okay? Essentially what we're defining here is somehow as a class that contains one thing. So what we're saying is it really has the value Homo sapiens rather than it has a value that's of type Homo sapiens. We're saying that it has the value Homo sapiens. So what does this mean? If we have person subclass of has value Homo sapiens on property species, and we add that Mary is of type person here, then we can entail that Mary species Homo sapiens. Again, the difference with some values from is that here we're entailing directly the value Homo sapiens. We're not entailing a value that is of type Homo sapiens, right? So in this case, we can entail that's Mary species Homo sapiens, as we see here. What about the other direction? If we have equivalence here, and we know that Mary has species Homo sapiens, then we can entail that Mary is of type person as well. Okay, another feature similar perhaps is the has self feature, but we can't express it using has value. So what does has self do? It states, for example, that if you have a class, that it has itself as a value for a property. So for example, a narcissist is a subclass of loves themselves. So they have themselves as a value for loves. So if we have narcissist, a subclass of has self true on property loves, and we have Michael type narcissist, okay, what can we entail? We can entail that Michael loves himself. Okay, so Michael loves Michael. If we define it as an equivalence, what happens here? Well, if we know that Michael loves Michael, then we can entail that Michael is a narcissist. Any questions or doubts? Okay, so the last kind of categorization of features are cardinality restrictions, which allow us to define a class with a given number of values for a property. And we can define an exact version of cardinality. For example, a person is a subclass of has precisely 2 biological parents, which means that if you're a person, you have precisely 2 biological parents. Although this is not actually 100% strictly true. but this is what this means. This is what this claim would mean. So here's how we write it in Turtle. Person subclass of cardinality 2 on property has biological parent. We can also have a max version of that where we specify a maximum, the class of things that have a maximum number of values for a property. So we can say that a monogamous, for example, is a subclass of the class having at most one current spouse. Okay, so this means that either a monogamist has a spouse, at most one, or has currently no spouse. So monogamous subclass of max cardinality 1 on property has spouse. And we also have min. So we can say that a parent is equivalent to something that has at least one child. Actually, this is a slightly different semantics to earlier. I assume that earlier that parents were human. Here, I'm not assuming that, but okay. So a parent is equivalent to having at least one child, effectively the class of things that have at least one child. So parent equivalent class min cardinality 1 on property has child. Okay, so here in this case, these cardinality restrictions, they count all values for a property. But there is one last category of definitions that we can do in OWL, which are qualified cardinality restrictions, which only count the values that are in a given class, in a second class that we will define. So as an example, biped refers to animals that have 2 legs, okay? So a biped is equivalent to the class of things having exactly 2 legs, 2 limbs that are legs, that are of type leg. So a human is a biped, even though it has 4 limbs, okay? But 2 of those limbs are arms and 2 of those limbs are legs. So we're only going to count the legs here. Okay? So this states that a biped is equivalent to the class of things that have precisely 2 limbs that are instances of leg. Okay, and here's the definition: biped equivalent class, qualified cardinality 2 on property has limb on class leg. We also have the max and min version of qualified cardinality restrictions. So we can say, for example, that a mafia family is a subclass of has at most one current member that is a godfather. So a mafia might have lots and lots of members, but what we're saying here really is that it can only have one member that's an instance of godfather. And that's defined here in this way. Max qualified cardinality 1 on property has current member on class godfather. So again, this thing here represents this class definition, which defines the things that have at most one current member that's an instance of godfather. And then we define mafia to be a subclass of that class. And min, we say that a twin has at least one sibling that is an instance of twin. So in this case, we have twin subclass of min qualified cardinality 1 on property sibling on class twin. So here, this tells us that if you're a twin, then there exists not only a sibling, not only that you have a sibling, but that at least one of your siblings is a twin, is also a twin. Any questions or doubts? In the chat? All good. All right. So just to clarify that, here I've presented kind of examples of what you can entail from the definitions, but these are really examples and they're not definitions in themselves, right? So we'll have to look at how to more formally define this. So there are other examples of entailments, and especially when we start to combine things, there can be, other things that we can entail that we haven't shown. So in general, the examples I've shown are the principal entailments that you can get from these features and illustrate what the features mean, but we haven't still really formally defined what the features mean. That will be a subject for the next class. But here, for example, if we have Vito Young as of type godfather, what we saw in this case for this definition, is that, okay, we'll know Vito's of type godfather, Michael's of type godfather, Vincent's of type godfather. However, we can also infer other things. For example, if we have Vito Young as of type godfather, then we can infer that Vito Young must be the same as Vito or Michael or Vincent. It must be equal to one of these things here. So just to clarify that, that the slides are examples. And with this sort of thing, we can do very complex reasoning with the features we've seen. Actually, with all of the features we've seen, it becomes undecidable. We could actually model a halting problem with this and ask if some program halts, for example. So and we can cover, for example, definitions of zebroids and of a variety of different domains, allowing for automated reasoning. So in this case, returning here, now we can see that we've seen all of the features necessary to express all of these things. In particular, these two here, subproperty, come from RDFS. A zebroid has exactly one parent, a zebra. That would be exact qualified cardinality. This again would be exact qualified cardinality. A zebroid is a subclass of equine or DFS, and equine has exactly two parents. That would be exact cardinality, unqualified in general cardinality. Two things cannot be related by sire and dam at the same time, and that would be property disjoint with. So now we have enough with RDFS NL to express all of these different claims here, which would allow us to entail that Z as a type zebroid. So that's all. So we've covered all the features, and in the next two classes, we'll have to dive a little bit into more into how it's defined and the semantics, how the semantics are formally defined, and as well as things like how we can do reasoning, questions of undecidability and so forth. So any questions? All good? Okay, so you probably want to get started with the lab. Just to briefly mention that the features you'll see today come before this slide, which is to say that the lab today is focused on these property axioms. So all of the questions should be answerable in the lab from these property axioms up to where you have this section divide class axiom. So, okay, so we'll start moving to Discord.